Hey folks, it's Mr. Woodward giving you an introduction to this voltage investigation. So the voltage investigation is going to be tied to the law of conservation of energy, and I'll trust that you can kind of read this introduction, but you will see conservation of energy applied in the idea of voltage. A couple of vocabulary clarifications. You are going to see two terms. The first is electric potential, which is often labeled V in equations, and then you're going to see change in electric potential, which is labeled, you can think of as delta V. Okay, what's the difference between electric potential and the change in electric potential? Well, here's a little helpful clarification, okay? So first, electric potential is referring to the electrical potential energy per charge at one specific point in a circuit, okay? So think about some point in a circuit, and going to the circuit construction kit, it could be like, this spot here, something, and say, okay, this spot has a specific electric potential, and the electric potential would be defined as the available potential energy per coulomb of charge at that spot. And of course, there would be no electric potential right now because there's no flow, but now there is. So that's electric potential, okay? Electric potential difference is similar, but here's how it's different, okay? So electric potential difference we call voltage, okay? And it is comparing 2 points. So you can only have an electric potential difference or a voltage across 2 points because it is measuring the change in electric potential, okay? And you can think of it as like, your change in electric potential is going to be the potential, the electric potential at some point. You can think of this as a final point minus an initial point, or, point 1 to point 2, or however you want to label those 2 points, okay? But it's a change in potential across 2 points. It is also measured, however, in volts. Just like, momentum or energy is measured in joules, but then change in energy would also be measured in joules. So electric potential is at 1 point, but voltage is the change in electric potential across 2 points. That should be a helpful clarification to you. All right, so now how do we jump into this? So in this investigation, you're going to build these 6 circuits plus that one, so that's 7. And starting with this first one. So you're going to build the circuit, and that one's going to look like this. If I close the circuit, now the light turns on. And then you're going to use a voltmeter here. You'll notice it has a black lead and a red lead, okay? And this is how you're going to apply the voltmeter. You're going to touch the different ends to this circuit. So you're going to start with the black lead here, and then you're going to take the red lead and you're going to touch it here, here, and here. And you're going to write down the electric potential that it's measuring. So here we go. We always start by calling the negative end of the battery 0 volts of electric potential. And then let's use the voltmeter to measure the rest, okay? So we're going to call this 0 here, and then if I touch it to the positive end of the battery, I get 9 volts, and then at this end of the light, I get 9, and then at this end of the light, you'll notice it changes to 0, okay? So let's write that down. So I got 9 volts, I got 9 volts, I got 0 volts. Okay, so based on what the voltmeter is showing me, okay, and then I want to determine the delta V, right, the change in electric potential across the battery and across the lights. So delta V here, and then a delta V here. And the way that I'm going to do that is through note number 3, okay? It says calculate the voltage difference across each circuit element, meaning, the final point minus the initial point. Note, conventional current flows in clockwise directions in all of the following diagrams, meaning this way. So VF is the point where charges exit an element, and VI is the point where charges enter an element. And what I mean by that is here. If you go back to the circuit construction kit, notice in the top right corner, you can actually just hide the current altogether. Or you can show it in two ways, from electron flow or conventional current flow, okay? And the voltmeter is programmed for conventional current flow. So we want to go this way. That means in conventional current, the current is flowing out of the positive end of the battery and into the negative end of the battery. And my understanding is that conventional current was invented before the electron was discovered. I think it was arbitrarily assigned by, I think, Ben Franklin and other early physicists before they knew what an electron was. All right, so then the change in electric potential is going to be the exit point minus the entrance point. So if I'm looking at the battery, the exit point is the positive end of the battery. The entrance is at the negative end of the battery, right? And then if I'm looking at the light, well, now the exit point is the negative, is this end of the light, and the entrance point would be there. So writing that down, here I would use 9 minus 0, and that gives me a delta V of 9 volts. And over here, though, using the conventional current direction, I would do this side minus this side, the exit minus the entrance. So this would give me negative 9 volts. All right, so that's the first one. Then you're going to continue that, moving to the 2 light, the 3 light, and then doing all the parallel circuits. And so I'll just show you how to set up the next one. For the next circuit, you're going to measure, you're going to put the red end here, 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 and the black end here. Taking your measurements, calculating the delta V across, and I'll show you where I want the delta V. Here, here, and here. At each circuit element, right? Every battery and every light. And then you'll do that down here. Notice that these two circuits are exactly the same, so you can just show the same thing for both of them. All right, good luck.